This story is about one of the quietest revolutions in modern science, about how the familiar picture of the cosmos gave way to another, larger, stranger, less cozy. There will be no shouting and no sensation here. There will be observation, reflection, and a calm acknowledgement that we now see differently, and that there is no going back from this new vision, however tightly you close your eyes. What is at stake here is not one planet, not one discovery, but a whole picture of the world that humanity lived with for several centuries. For a long time, it seemed that our solar system was an example of how star systems in general are arranged, that we were a model, not an exception, that somewhere nearby there would surely be found familiar features, recognizable orbits, familiar distances. On this rested intuition, the very intuition that helps the mind not to be lost before the abyss. And it was precisely this intuition that had to be slowly released. When observational instruments made it possible to peer into other stellar courtyards, it turned out that what was seen fit poorly into the old templates. The familiar classifications ceased to work. Words had to be chosen anew. And together with words, the sense of our own place changed. No longer central, no longer exemplary, no longer the most important. This story is about how such a shift is inhabited, about what it means to speak of distant worlds we will never see up close, and about how science keeps its composure when the familiar map turns out to be only a small corner of something far greater than itself. And you, what do you choose when you learn that the world is arranged differently than it seemed to you? Do you narrow the description down to the familiar? Or do you agree to live with the fact that much will remain indirect, imprecise, inferable from faint traces? What matters more to you, a clear answer or an honest, "we do not yet know"? Listen, this story is about that. For a long time, we considered our solar system, if not unique, then at least typical. The planets around the sun seemed not a chance concurrence of circumstances, but something like a norm, an example of how stellar systems in general are arranged. What exactly changed this view, and why did the change occur precisely in recent decades? An exoplanet in modern astronomy is a planet that revolves around a star beyond the solar system. The definition sounds simple, almost mundane. But behind it lies a deep shift in how science understands the arrangement of planetary systems and the place of our own system among them. Relatively recently, exoplanets were not discovered objects but merely hypothetical ones, an assumption no one could verify. And the very fact of their detection became one of the most significant turning points in astronomy of recent decades. For a long stretch of time, planets were regarded as a rare, possibly unique phenomenon linked to the special conditions of the formation of our own sun. Observational instruments did not allow direct detection of planets around other stars, and so scientific ideas were built primarily on theoretical reasoning. These arguments did not rule out the existence of other planetary systems, but they could not confirm them observationally either. In this sense, exoplanets long remained part of supposition rather than of established knowledge, a beautiful idea without proof. The situation began to change as observational methods and data analysis were refined. Improvements in measurement precision opened access to subtle effects associated with the presence of planets around other stars. These effects did not manifest as direct images. They expressed themselves through influence on the radiation and motion of the stars themselves. It was precisely the indirect nature of these observations that determined the specifics of the entire field of exoplanet research from the very beginning and up to the present day. An exoplanet in a scientific context is not required to resemble Earth or any other planet of the solar system. Already, the first discoveries showed that the diversity of planetary objects is significantly wider than anyone had assumed. Many of the planets found have no direct analogs in our system, neither in mass, nor in orbital parameters, nor in physical conditions. This broadened the very notion of what configurations of planetary systems are possible in the universe. Exoplanets have ceased to be perceived as exceptions and have come to be regarded as a natural result of the processes of star formation and of the disks of matter around them. Modern science proceeds from the assumption that the formation of planets is a natural side effect of star formation. However, the specific characteristics of planetary systems depend on many factors: the mass of the star, the composition of the surrounding matter, the dynamics of the early stages of evolution. Exoplanets in this context serve as observational material for testing and refining these ideas. The transition from theoretical assumption to observational confirmation had important methodological consequences. Astronomy encountered the necessity of interpreting data in which the signal from a planet is extremely faint compared with the star's radiation. This required the development of statistical methods, long-term observational programs, and an extremely cautious attitude toward the interpretation of results. In the field of exoplanets, the fundamental distinction between detecting an object and understanding its properties is especially clearly manifested. These are two different tasks. Exoplanets are detected in the context of specific stellar systems, not in isolation. This means that their study is inevitably linked with the study of their stars. The properties of the star determine the parameters of the orbit, the temperature conditions, and the dynamic stability of the planets. Therefore, exoplanet astronomy is by its very nature an interdisciplinary field, combining knowledge of stars, of the interstellar medium, and of the dynamics of gravitational systems. From the very first steps, it became clear that exoplanets do not form a uniform category. Among them are found massive objects, close in their properties to stars, and small bodies comparable in size to Earth. The boundary between planets and other objects is not always clear-cut, and its definition is of a working nature. This reflects a general principle of astronomy, in which classifications serve as an instrument of analysis, and not as a strict reflection of natural boundaries. Exoplanets have also changed the notion of typical orbital configurations. Before their detection, the solar system was often regarded as an example of typical planetary architecture. Observations of other systems have shown that this assumption is not necessarily correct. Systems are encountered with very compact orbits, with massive planets near the star, and with configurations that are difficult to explain on the basis of early models. Science has been faced with the task of revising ideas about the formation and migration of planets. In most cases, only certain parameters of an exoplanet are known: mass, radius, or orbital period. Many other characteristics are derived indirectly and are attended by substantial uncertainties. This requires constant refinement of models and revision of conclusions as new data accumulate. Exoplanet astronomy develops not as a linear accumulation of knowledge, but as a process of gradual approach to a more complete picture. And this is the normal course of science. Observations show that planets are encountered around a significant fraction of stars. However, the estimate of this fraction depends on the methods used and on which types of planets are counted. Science strives not for an exact number, but for an understanding of ranges and regularities, which corresponds to the general approach to the study of complex systems. The study of exoplanets is not reduced to the search for objects potentially suitable for life. Although this aspect often attracts attention, the scientific task is considerably wider. Exoplanets are considered as physical objects subject to the general laws of nature. Their diversity makes it possible to test these laws in conditions not represented in the solar system. In this sense, each exoplanet is a separate experiment of nature. The existence of exoplanets is reliably confirmed. However, details of their internal structure, atmospheres, and evolution often remain the subject of discussion. Different models can explain the same observations with varying degrees of success. And this is not a sign of science's weakness, but a reflection of the complexity of the objects under study. Exoplanets raise the question of how universal the processes are that led to the formation of the solar system. The observed diversity of systems indicates that universal mechanisms may be realized differently depending on conditions. Thus, exoplanets in the modern scientific understanding are not merely planets around other stars, but a whole class of objects that has radically expanded the notion of planetary systems. Their study is associated with indirect methods, a high degree of uncertainty, and a constant revision of models. A calm and consistent examination of these objects allows one to see in them not a sensation, but a natural result of the evolution of stellar systems and an important source of knowledge about the structure of the universe. But before moving on, how at all can one see a planet that does not shine on its own and hides in the shadow of its own star? We have never seen most exoplanets directly. All we have is shadows, the faint trembling of stars, the slightest deviations in the light. How from these grains is knowledge of other worlds assembled? The detection of exoplanets represents one of the most complex tasks of observational astronomy. Planets do not emit their own light in the optical range and are located against the background of significantly brighter stars. This makes direct observation in most cases impossible. Therefore, the development of exoplanet science is linked above all with indirect methods, each of which relies on the measurement of secondary effects caused by the presence of a planet. One of the most widely applied approaches is based on the analysis of the motion of the star. A planet and a star form a gravitationally bound system in which both bodies revolve around a common center of mass. Although the motion of the star is significantly weaker, it can nonetheless be recorded with sufficient measurement precision. The observed change in the velocity of the star along the line of sight is interpreted as a sign of the presence of an orbital companion. This method allows one to estimate the mass of the planet and the parameters of its orbit. However, it is sensitive above all to massive objects and to certain orientations of the system. Another important method is associated with the periodic dimming of a star's brightness. If the orbit of a planet is oriented so that the planet passes between the star and the observer, part of the starlight is temporarily blocked. This leads to a small but measurable decrease in brightness. Analysis of such changes allows one to determine the radius of the planet and to refine the parameters of the orbit. However, this method is applicable only to a limited number of systems, since it requires a specific geometry of observation. The combination of different methods plays a key role in obtaining more complete information. Measuring the mass and radius of the same planet allows one to draw conclusions about its average density, which in turn provides the possibility of supposing whether the object is predominantly gaseous or contains a significant proportion of solid components. Nevertheless, such conclusions remain generalized and do not reveal the internal structure of the planet in detail. There also exist other methods of detection, applied more rarely or under more specialized conditions. Some are based on the analysis of changes in the position of the star on the sky, others on the amplification of the light of a distant star under the action of the gravity of an intermediate object. Each of these approaches has its own advantages and limitations related to sensitivity, range of applicability, and interpretation of the data. Taken together, they form a set of instruments that allow different types of planetary systems to be covered. Each method of detection imposes its own limitations on the sample of found exoplanets. The observed diversity of planets partly reflects the real properties of planetary systems, and partly the features of the methods used. Massive planets on close orbits are detected more easily than small planets on distant orbits. Therefore, statistical conclusions require careful correction for observational effects. The observability of exoplanets is also limited by the quality of the data and the duration of observations. Many planets have orbital periods exceeding the lifetime of observational programs. In such cases, their presence may remain unnoticed or manifest itself only partially. This means that modern catalogs of exoplanets represent an incomplete slice of the real distribution of objects, and science takes this incompleteness into account, although it is impossible to eliminate completely. Particular difficulty is presented by the interpretation of faint signals. Changes in the brightness or velocity of a star may be caused not only by planets, but also by internal processes of the star itself. Surface activity, pulsations, and magnetic phenomena are capable of producing effects outwardly similar to planetary signals. Distinguishing these factors requires the accumulation of data, the use of additional indicators, and statistical analysis. Even with all this, the probability of an ambiguous interpretation remains. The development of detection methods was accompanied by a gradual increase in measurement precision, which expanded the range of detectable objects, including planets of smaller sizes and masses. However, the growth of sensitivity has also led to an increase in the number of borderline cases, where the signal is at the level of noise. In such situations, science is forced to work with probabilities, not with unambiguous statements. The detection of an exoplanet does not always mean the immediate recognition of its existence. Scientific practice uses a system of confirmations, including repeated observations and independent methods of analysis. Only after passing these stages is an object included in the list of confirmed exoplanets. This process can take a long time and reflects the cautious character of the scientific approach. Limitations of observability are also linked to the distance to stellar systems. Most of the exoplanets discovered are located in the relatively close vicinity of the solar system by cosmic standards. More distant systems remain difficult to access for detailed research. This means that exoplanet astronomy, to a significant degree, studies a local fragment of the galaxy, and the generalization of results to the entire universe requires additional assumptions. Methods for detecting exoplanets continue to develop. Improvements in instruments and refinements in data processing allow the threshold of sensitivity to be gradually lowered. However, even with ideal technologies, fundamental limitations remain, associated with the geometry of observations and the physical properties of the systems. A complete and exhaustive description of all exoplanetary systems is in principle unattainable. Methods of detection form the foundation of knowledge about these objects, at the same time defining the boundaries of the observable. An exoplanet is studied through indirect effects, statistics, and models, and not through direct perception. An awareness of these limitations is a necessary condition for a balanced understanding of what science actually knows about exoplanets and where the regions of uncertainty begin. And when we began to look in a new way, it turned out that the planets found do not resemble anything from our experience. Astronomers expected to find other solar systems, orderly, resembling our own. Instead, they discovered something for which we initially did not even have suitable words. The first exoplanets discovered showed straight away that planetary systems can be arranged significantly differently from the solar system. This led to the revision of many notions that had previously seemed almost self-evident. Classifications based exclusively on the examples of familiar planets turned out to be insufficient for describing the new diversity of objects. Exoplanets demonstrated that the nature of planetary bodies admits a far wider spectrum of states and configurations. One of the most striking discoveries was the existence of massive planets orbiting very close to their stars. Such objects have no direct analogs in the solar system. Their presence called into question the notion that large planets necessarily form and remain on distant orbits. Within the framework of modern models, it is supposed that such planets could have formed at large distances and then gradually shifted closer to the star under the action of interactions with the surrounding matter or with other planets. However, the details of these processes remain the subject of research and are not in all cases unambiguously reconstructed. Alongside massive objects, exoplanets have been discovered with sizes and masses intermediate between Earth and the giant planets. In the solar system, such bodies are absent, and this was for a long time perceived as a universal feature of planetary systems. Exoplanetary observations have shown that this is rather a particular case. These intermediate planets represent a separate class of objects with diverse properties. Their internal structure and composition can differ substantially, even if the sizes appear similar. The diversity of exoplanets manifests itself not only in mass and radius, but also in density. Planets of the same size can have completely different densities, which indicates differences in composition. Some contain a significant proportion of light components, others consist predominantly of heavier substances. However, the connection between the measured parameters and the real structure of a planet remains indirect. Average density gives only a general idea and does not allow the internal structure to be determined unambiguously. Exoplanets also demonstrate a wide range of orbital parameters. Systems have been discovered with a very compact arrangement of several planets, where the orbits lie at distances significantly smaller than the orbit of the planet closest to the Sun. Such configurations require a stable dynamic balance and point to a complex history of formation. There also exist systems with strongly elongated orbits, where the distance of the planet from the star changes substantially over the course of a single revolution. These features raise questions about the mechanisms of stabilization and long-term evolution. The classification of exoplanets by analogy with the planets of the solar system is gradually giving way to more functional approaches. Instead of attempts to find direct analogs, description by physical parameters and conditions is used. Planets are grouped by mass, radius, density, temperature regime, and orbital characteristics. Such an approach makes it possible to systematize the observed diversity without imposing preset forms upon it. The observed diversity of exoplanets partly reflects the limitations of detection methods. Certain types of planets are more easily identified than others, and are therefore more broadly represented in the data. This means that the real distributions may differ from the observed ones. Science strives to correct these distortions by means of statistical methods. However, it is impossible to eliminate them completely. Therefore, any conclusions about the typicality of one or another planetary property are formulated with caution. The diversity of exoplanets also raises the question of the boundaries of the very concept of planet. In a number of cases, the objects discovered lie on the border between planets and other types of bodies. Their classification depends on the chosen criteria, which are themselves of a working and conditional character. This reflects a more general principle, according to which natural objects form continuous series of properties, and scientific categories serve as an instrument of ordering, not as rigid frames. Exoplanetary systems often demonstrate complex interconnections between planets. Orbital resonances and other forms of dynamic linkage indicate that the planets evolve jointly, influencing one another. These interactions may have played a key role in shaping the observed structure of the system. Analysis of such configurations allows one to draw conclusions about the early stages of evolution. However, these conclusions remain probabilistic and depend on the models used. The diversity of exoplanets does not contradict the existing physical laws. On the contrary, it demonstrates how differently these laws can be realized depending on the initial conditions. Exoplanets expand the empirical base on which models of the formation and evolution of planetary systems are tested. In this sense, each new system adds yet another variant of the realization of general principles. The modern understanding of the diversity of exoplanets remains incomplete. Many classes of objects are represented only by a limited number of examples, and some parameters are measured with large uncertainties. Classifications will be refined and revised as data accumulate. Such a process of revision is not a sign of the instability of knowledge, but a natural stage in the development of science. Exoplanets have demonstrated that planetary systems can be arranged far more diversely than had previously been assumed. And this diversity requires a rejection of narrow analogies and a transition to more flexible, parametric descriptions. But size and orbit are not everything. These worlds have something hidden even deeper: air, gaseous envelopes, chemistry. Through the light of a distant star, the envelope of an alien planet shines through. This is not a metaphor. This is literally how we study the chemistry of worlds thousands of light years away from us. The study of the atmospheres of exoplanets represents one of the most complex and at the same time most informative directions of modern astronomy. The atmosphere of a planet, if present, plays a key role in the formation of the observed properties of the object and reflects the history of its evolution. However, in the case of exoplanets, we are dealing not with direct observation, but with an extremely subtle analysis of changes in the star's radiation passing through the planetary envelope or reflected from it. The atmosphere of an exoplanet is not an independent object of observation. Its presence is revealed through its influence on the spectrum of the star or the system as a whole. During the transit of a planet across the disk of the star, part of the starlight passes through the planet's atmosphere. In this case, certain wavelengths are attenuated more strongly than others, depending on the composition and structure of the gaseous envelope. Analysis of these changes allows one to draw conclusions about the presence of one component or another. However, such conclusions always bear a probabilistic character. Methods of spectral analysis of the atmospheres of exoplanets require extremely high precision. Changes in the signal often amount to fractions of a percent or even less. This means that any noise associated with the instruments, with stellar activity, or with observing conditions can substantially affect the result. Interpretation of atmospheric data requires strict statistical processing and repeated verification. The detection of atmospheric components does not mean full knowledge of the properties of the atmosphere. The observed spectral features depend not only on the chemical composition, but also on temperature, pressure, the distribution of clouds, and the dynamics of the atmosphere. Different combinations of these factors can lead to similar observational effects. As a result, science often deals not with unambiguous answers, but with sets of admissible models. The atmospheres of exoplanets demonstrate significant diversity. Some objects have dense gaseous envelopes. Others have rarefied or unstable atmospheres. There are planets on which the atmosphere is subjected to intense action from the star's radiation and gradually disperses into cosmic space. Such processes are especially characteristic of planets located close to their stars. However, the rate and mechanisms of atmospheric loss depend on many parameters and remain the subject of active research. The atmosphere of an exoplanet is not always a long-lived structure. Over the course of a planet's evolution, its gaseous envelope can change substantially. The loss of light components, changes in chemical composition, and the redistribution of energy lead to transitions between various atmospheric states. These transitions may be gradual, but their result is a qualitatively different state of the planet. Particular complexity is presented by the study of the atmospheres of small exoplanets. Their influence on the star's radiation is significantly weaker than that of massive objects. Therefore, the data on such planets are limited and subject to large uncertainties. Nonetheless, it is precisely these objects that are of particular interest, since they make it possible to investigate the range of planetary conditions not represented in the solar system. The atmosphere of an exoplanet is not necessarily analogous to that of Earth. The presence of certain gases should not automatically be interpreted as a sign of similar conditions. Chemical reactions, photochemistry, and the dynamics of the atmosphere may differ substantially at different temperatures and pressures. Science regards the atmosphere as a physical system subject to general laws, but realizing them under specific conditions, without direct analogies with what we know from Earth. The study of the atmospheres of exoplanets is closely linked with the development of observing instruments. Improvements in spectral resolution and the stability of instruments allow the range of accessible data to be gradually expanded. However, even under the most favorable conditions, a fundamental limitation remains. The atmospheres of exoplanets are observed indirectly through the influence on the light of the star. Interpretation will therefore always depend on the model and on the assumptions adopted. Different models can interpret the origin of one or another spectral feature in different ways, and in scientific practice, such alternatives are considered in parallel, without premature exclusion. This makes it possible to preserve the flexibility of interpretation and to refine it as data accumulate. The atmospheres of exoplanets serve as an indicator of the interaction of the planet with the star. Radiation, stellar wind, and magnetic fields exert a substantial influence on the structure of the atmosphere. These interactions form a complex system of feedback loops, determining the long-term evolution of the planet. A quantitative description of such processes remains a difficult task, since it requires taking many parameters into account. Knowledge of the atmospheres of exoplanets is still fragmentary. For most planets discovered, the atmosphere is either not studied or described only in the most general terms. Nonetheless, even these limited data have already made it possible to substantially expand the notion of the possible states of planetary envelopes, and have shown that the atmosphere is a dynamic and changeable part of the planet, and not a static envelope. The atmosphere becomes the window through which science attempts to peer into the internal and evolutionary processes of the planet. A calm and consistent examination of these data makes it possible to understand not only what is already known, but also how large the region of uncertainty remains in the description of the atmospheres of exoplanets. But knowing the chemistry of the air, we do not yet know how the planet itself moves, and why it turned out to be precisely where it is now. Planets have not always been where we find them. Some of them have traveled through their entire system over millions of years before taking their present place. The orbital dynamics of exoplanetary systems represents a key to understanding their current state and their past evolution. The observed parameters of orbits, periods of revolution, eccentricities, mutual inclinations, are the result of prolonged processes that have taken place since the formation of the system. These parameters are not fixed once and for all. They change under the action of gravitational interactions, which can be weak and gradual or lead to noticeable rearrangements of the configuration. A planetary system forms within a protoplanetary disk, where matter is distributed unevenly and is in constant motion. In this medium, the orbits of nascent planets are not isolated trajectories. They form and change in an environment saturated with gas and solid particles. The interaction of a planet with the disk leads to an exchange of angular momentum, which can cause a shift of the orbit. This process has received the general name of planetary migration and has become one of the central elements of modern models. Migration is regarded as a probable mechanism explaining the presence of massive planets on close orbits. Interaction with the disk is capable of gradually changing the distance of a planet from the star. The rate and direction of such a shift depend on the mass of the planet, the density of the disk, and its temperature. However, the details of these processes remain complex and depend on parameters that are difficult to measure directly. Therefore, migration is considered not as a universal scenario, but as one of the possible paths of evolution. After the dissipation of the gaseous disk, the dynamics of the system are determined predominantly by gravitational interactions between the planets. These interactions may be stable for a long time if the configuration is close to equilibrium. However, even small perturbations are capable of accumulating and, in time, leading to noticeable changes. In some systems, signs are observed that the orbits of the planets continued to evolve even after the completion of the main stage of formation. One of the manifestations of complex dynamics is orbital resonances. They arise when the periods of revolution of the planets are related by simple numerical ratios. Under such conditions, the gravitational influence of the planets is amplified and acquires a regular character. Resonances can contribute to the long-term stability of the system, fixing the relative position of the orbits. In other cases, they are capable of leading to an amplification of perturbations and to instability. The observation of resonant configurations provides important information about the past interaction of the planets. Exoplanetary systems often demonstrate high values of orbital eccentricity. In the solar system, strongly elongated orbits are rare, and this was for a long time perceived as a typical feature of planetary systems. Observations of exoplanets have shown that this assumption is not universal. Elevated eccentricities may be the consequence of gravitational interactions between planets, as well as the result of external influences from other stars. To establish the precise cause for each system is often impossible. An important factor of dynamical evolution is the presence of additional bodies that may remain unobserved. Even comparatively small objects are capable of influencing the orbits of the planets discovered, changing their parameters over long periods of time. This means that the observed configuration of a system may be only a part of a more complex structure. Science takes this possibility into account. However, direct confirmation of such hidden components is far from always available. The dynamical history of exoplanetary systems is closely linked with the stability of orbits. Not every configuration is capable of being preserved for billions of years. Numerical models show that many initial states lead to rearrangements, to the approach of planets, to ejections from the system, or to absorption by the star. The systems observed represent those configurations that turned out to be stable, or that passed through unstable phases and transitioned into a new equilibrium. Instability, moreover, does not necessarily mean a rapid and dramatic process. In many cases, changes occur slowly and accumulate over long periods of time. To an outside observer, a system may look stable, although from the point of view of dynamics, it is in a state of gradual drift. This underscores the importance of taking timescales into account in the interpretation of orbital parameters. Orbital dynamics also influences the conditions on the planets themselves. Changes in the distance from the star and in the shape of the orbit lead to variations in the energy balance, which can be reflected in the atmosphere and internal state of the planet. However, the connection between dynamics and physical conditions is complex and mediated by many factors. Science does not yet possess the full set of instruments for an unambiguous description of these connections. The study of the orbital evolution of exoplanetary systems relies on a combination of observations and modeling. Observations provide the current parameters, and models make it possible to investigate the possible paths that led to this state. The current position of a planet is not a final point, but a temporary episode of a long history that began in the protoplanetary disk and continues to this day. If the orbit determines the conditions, then what are they on the surface of these wandering worlds? We can name the temperature of an exoplanet, but this is not a measurement. This is the result of a mathematical model, behind which are hidden dozens of unknown variables. The surface of an exoplanet, if it exists at all in the customary physical sense, is formed not by a single parameter, but by the complex interaction of orbital geometry, the properties of the star, and the internal characteristics of the planet itself. The main source of energy for an exoplanet is the radiation of its star. The amount of heat received is determined by the distance to the star and its luminosity. However, even at the same average level of irradiation, real conditions can differ substantially. The shape of the orbit, the tilt of the rotational axis, the speed of daily rotation, each of these parameters influences how energy is distributed over the surface and changes with time. These parameters rarely lend themselves to direct measurement, which introduces significant uncertainty into any estimate of the temperature regime. The temperature of an exoplanet cannot be measured the way one measures, say, the brightness of a star. It is derived from models of thermal balance, which take into account the reflectivity of the surface, the possible presence of an atmosphere, and its properties. Different combinations of these parameters can yield the same average values of temperature, which is precisely why science works not with exact numbers, but with ranges of admissible states. The atmosphere, if it is present, plays a key role. It redistributes energy, smoothing the contrast between the illuminated and shadowed sides of the planet. In the absence of an atmosphere, the difference between the daytime and nighttime surface can be enormous, especially on planets revolving close to their star. However, the degree of this leveling depends on the composition of the atmosphere, its density, and its dynamics. And these parameters are most often either unknown or determined only approximately. Planets on elongated orbits find themselves in a particularly complex situation. Over the course of a single revolution, they experience significant changes in energy balance. This means that conditions on such planets can change cardinally even at relatively moderate average values. The stability of conditions is not reducible to a simple question of distance from the star. What matters, too, is the stability of the orbit itself and the character of its long-term evolution. The question of the stability of conditions over time turns out to be one of the most difficult. Even if at the present moment the parameters of an exoplanet admit the existence of a certain temperature regime, this does not mean that it has been preserved or will be preserved indefinitely. The evolution of the star, gradual changes in the orbit, slow processes in the atmosphere, all this is capable of leading to irreversible changes stretched over billions of years. Science in this context considers not instantaneous snapshots, but time intervals and the probability of their preservation. The very concept of a surface is by no means applicable to all exoplanets. Many of the objects discovered are gas giants or possess envelopes so dense that the boundary between the atmosphere and the internal layers becomes conditional. For such planets, speaking of surface conditions in the customary sense has no basis. We are speaking of transitional layers with gradually changing properties, difficult to describe by simplified models. Internal sources of heat also contribute to a planet's energy balance. The radioactive decay of elements in the interior, residual heat from the formation of the planet, tidal effects, all of this can influence the energetics of the system. For some planets, this contribution can turn out to be quite substantial in comparison with external irradiation. However, to estimate such processes without knowledge of the planet's internal structure is impossible, and the structure, as a rule, remains unknown. Stability of conditions in the physical sense means the ability of a system to preserve its characteristics under small perturbations. An exoplanetary system may be in a state where insignificant changes in parameters do not lead to abrupt transitions. But when certain thresholds are exceeded, qualitative jumps become possible. The determination of precisely these thresholds remains one of the key tasks of theoretical modeling. The properties of a star impose yet another layer of uncertainty. The spectral composition of the radiation, activity, and evolutionary path of the star exert a substantial influence on the energy conditions of a planet. Even at the same luminosity, differences in spectrum can be reflected differently on the atmosphere and surface. Conditions on exoplanets cannot be described by a single universal scheme. Each system represents a specific combination of factors, realized under concrete circumstances. Exoplanet science moves from the estimation of separate parameters to the construction of coordinated models of conditions, taking into account the interaction of orbital dynamics, atmosphere, and energy balance. But the results of such models depend on the initial assumptions and on the quality of the data. These models are an instrument for investigating possible states and not a precise description of a specific planet. The region of uncertainty in the estimation of surface conditions remains significant and, in principle, unremovable at the present stage of research. Everything that is on a planet, its surface, its air, its envelopes, is matter. And each atom has its own history. Each atom in the atmosphere of an exoplanet carries a trace of some event, of coalescence with the disk, of an impact, of a chemical reaction under the action of the stellar wind. We read this history bit by bit from the spectrum, and in it, as in a geological cross-section, all the stages of the past are imprinted. The chemical composition of exoplanets is one of the main sources of information about the processes of the formation and evolution of planetary systems. Unlike orbital parameters or mass, chemical characteristics reflect not dynamics, but the history of matter, where it came from, and through what conditions it passed. The study of this diversity relies on indirect data and requires a consistent, step-by-step analysis. At the stage of the formation of a planet, its chemical composition is determined by the properties of the protoplanetary disk. Temperature, density, and the distribution of elements in the disk change with distance from the star, and therefore the matter condensing in different zones has a different composition. Planets formed in different regions of the disk initially bear different chemical imprints, but subsequent evolution is capable of substantially altering this initial set. The migration of planets plays an important role in this process. If a planet shifts from one zone of the disk to another, it can capture matter of a different composition, accumulating it in its interior and envelopes. As a result, the chemical characteristics of a planet may not correspond to its present position in the system, which substantially complicates the interpretation of observations and requires the entire dynamical history of the system to be taken into account. The atmospheres of exoplanets are the main object of chemical analysis, since it is precisely through atmospheric spectra that one manages to obtain information about the presence of various compounds. However, the observed chemical features reflect not only composition, but also physical conditions. Temperature, pressure, and the vertical structure of the atmosphere influence which molecules appear in the spectrum and how distinctly. The interpretation of chemical data always relies on model assumptions. The chemical composition of the atmosphere does not necessarily coincide with the composition of the whole planet. The atmosphere may be secondary, formed as a result of the outgassing of internal layers or under the action of external processes. In that case, it reflects not the initial matter of the planet, but the result of its evolution. This distinction is fundamental for understanding where precisely the observed chemical components come from. Chemical processes in the atmospheres of exoplanets often are in a non-equilibrium state. The radiation of the star causes photochemical reactions that change the composition at different altitudes, while the mixing of the atmosphere transports substances between layers with different conditions. The observed composition is not a static slice, but a dynamic picture, constantly changing under the action of external and internal factors. The chemical diversity of exoplanets is also linked with their mass. More massive planets retain light components more effectively, whereas less massive bodies can gradually lose them, especially if the star is active and its radiation intensely acts on the atmosphere. This process changes the composition of the envelope with time and is capable of leading to a transition between entirely different chemical regimes. However, the rate of such changes depends on many factors and remains the subject of active research. Particular difficulty is presented by the interpretation of chemical data for small exoplanets. Their atmospheric signals are extremely faint, and the space of admissible combinations of parameters is enormous. In such cases, science limits itself to the formation of possible scenarios rather than of concrete descriptions. This reflects the probabilistic character of knowledge in this area. The comparison of the chemical characteristics of different planets makes it possible to reveal general tendencies and differences, but such analysis requires careful account of observational limitations. Without this, there arises the risk of ascribing physical meaning to differences that are in fact generated by the peculiarities of measurement methods, not by the real properties of the objects. The chemical diversity of exoplanets is not a set of anomalies and exceptions, but a natural result of the evolution of matter in protoplanetary disks and of subsequent physical processes. The atmospheres and envelopes of planets are dynamic chemical systems whose properties depend on many factors. Regarding these processes as the realization of general physical and chemical regularities under different conditions makes it possible to see in the chemical diversity not a riddle, but a natural outcome of the interaction of matter and time. And when researchers begin to assemble all of this together, a question inevitably arises that is difficult to bypass. Could conditions suitable for life exist there? The habitable zone is not a place where life is certain. It is a place where we cannot yet rule it out. A thin but fundamental difference. The concept of habitability in exoplanet science is one of the most discussed and at the same time one of the most limited. It arose as an attempt to formalize the conditions under which certain physical states of the environment can be preserved on a planet. In the scientific sense, habitability is not a statement about the presence of life, but a working category for describing ranges of parameters under which certain processes are not excluded from the point of view of physics and chemistry. Most approaches to habitability are based on the analysis of energy balance. The possibility of the existence of a stable state of matter under given conditions of temperature and pressure is considered. However, such an analysis inevitably simplifies the real picture. It relies on a limited number of parameters and does not take into account the whole complexity of planetary systems. Therefore, habitability in a scientific context is always regarded as a conditional and probabilistic concept, no more. The range of distances from a star within which a planet can receive energy within certain limits is often used as a reference point, but not as a strict boundary. Real conditions on a planet may differ substantially from the calculated ones, due to the influence of the atmosphere, the reflectivity of the surface, or internal sources of heat. The presence of a planet within such a range is neither a necessary nor a sufficient condition for the stability of a concrete environment. Habitability is not a permanent property of a planet. A planet may end up in suitable conditions only briefly and then pass into another state under the action of the star's evolution, changes in orbit, or gradual atmospheric processes. To speak of sustained habitability in that case is not possible. Science considers not momentary states, but time intervals and the probability of their preservation. The atmosphere plays a central role in any discussion of the boundaries of habitability. It determines the redistribution of energy, the protection of the surface from radiation, and the chemical environment on the planet. But the presence of an atmosphere is not guaranteed and is not unchanging. Atmospheres can form, be rearranged, and gradually lose their components under the action of the stellar wind. To estimate these processes quantitatively for specific exoplanets is extremely difficult. The concept of a surface, as has already been noted, is not applicable to all planets. For objects without a clear boundary between the atmosphere and internal layers, the discussion of habitability in the customary sense loses physical meaning. This broadens the understanding that habitability is not a universal characteristic. It is applicable only to certain classes of objects. The concept of habitability is shaped in the context of terrestrial experience. It reflects knowledge of the processes realized in one specific system, our own. Exoplanetary observations show that planetary environments can differ radically from Earth's in the most varied parameters and at the same time remain physically stable. This raises the question of expanding or revising the criteria used. However, any such revision runs into the limitations of the available data. There exist alternative approaches to habitability, which focus not on specific substances or temperature thresholds, but on the stability of energy and chemical processes as such. These approaches are in a stage of development and have not yet received sufficient observational support. However, they reflect the striving to go beyond anthropocentric criteria. From a scientific point of view, habitability is an instrument of classification, not a goal of research. Exoplanets are studied above all as physical objects subject to general laws. An exaggeration of the significance of the question of habitability is capable of distorting priorities and leading to a wrong interpretation of the data. Recognition of the limitations of this concept, on the contrary, makes it possible to formulate conclusions more precisely and to avoid unjustified generalizations. Modern models of habitability are becoming increasingly complex, incorporating the evolution of the star, the dynamics of the orbit, and changes in the atmosphere. But the increase in the number of factors taken into account does not eliminate the fundamental uncertainty. Many parameters remain unknown or weakly constrained, and therefore the results of modeling should be perceived as an investigation of possible scenarios and not as a prediction of real conditions on a specific planet. Habitability appears not as a statement about the reality of processes, but as a description of the ranges of conditions admitted by physics. No more. But no planet exists in isolation. Behind each of them stands the history not merely of one star, but of a whole galaxy. Looking at an exoplanet, we look not only into space, we look also into the past, sometimes billions of years back, to the conditions from which it was once born. Exoplanets are inseparable from larger cosmic processes. Their properties and evolution are closely linked with the history of the stars around which they revolve, as well as with the conditions of the galactic environment in which these stellar systems formed. Consideration of exoplanets in this context makes it possible to go beyond the framework of individual planetary systems and to see a broader picture of the connections between different levels of the organization of matter. A star is the central element of a planetary system. Its mass, chemical composition, and evolutionary path influence the formation of the protoplanetary disk and all further development of the planets. Changes in the properties of the star with time lead to changes in the energy and radiation environment, gradual but capable over long timescales of qualitatively changing the state of planetary environments. The chemical composition of a star reflects the conditions of the galactic environment at the moment of its formation. The matter from which the star and its planets formed is the result of the work of preceding generations of stars and of the processes of the redistribution of elements in the galaxy. Exoplanets in this sense carry information about the chemical history of their galactic vicinity. Differences in the composition of planetary systems may be linked not only with local conditions, but also with the larger-scale evolution of the galaxy. The probability of the presence of planets depends on the characteristics of the star. This is confirmed by observations. However, these dependencies are not absolute. They manifest themselves statistically and admit exceptions. The formation of planets is a probabilistic process sensitive to many factors. Exoplanets appear as the result of a combination of universal mechanisms and random initial conditions. The galactic environment influences planetary systems not only through chemical composition. The density of stars, the frequency of close interactions, and the level of background radiation are capable of exerting an effect on the long-term stability of systems. In more dense regions of the galaxy, gravitational perturbations from neighboring stars can change the orbits of planets or even lead to the loss of individual objects by the system. Such events occur rarely, but on large timescales they are capable of leaving a noticeable trace. The evolution of the galaxy is also linked with changes in the conditions of star formation. In different epochs of galactic history, the properties of protoplanetary disks could differ substantially, and this means that exoplanets formed in different periods may have systematic differences in composition and structure. Modern observations make it possible to trace these tendencies only partially. The available sample of exoplanets covers certain types of stars and distances, which limits generalizations. Exoplanetary systems can be regarded as peculiar archives of stellar evolution. Their orbital configurations, composition, and distribution of masses store information about past interactions with the disk and about subsequent dynamical processes. But this archive is incomplete and noisy. Many details of the history are lost or masked by later changes. Science in this context works with reconstructions and not with direct testimonies. The galactic environment also determines the background flux of radiation and particles acting on planetary systems throughout their entire lives. These factors can play a role in the long-term evolution of atmospheres and surfaces. However, their quantitative estimation remains a complex task. Most such processes occur on timescales significantly exceeding the duration of any observing programs. Exoplanets are a part of a multi-level system where local processes are interwoven with global ones. Their properties cannot be fully understood by considering only a single planet or even a single stellar system. It is necessary to take into account the context of the larger structure in which these systems exist. Scientific models that link exoplanets with the evolution of stars and galaxies are in a stage of development. They form the framework for the interpretation of the observed diversity, but do not provide final answers. Uncertainty within these frameworks is recognized as an inherent part of knowledge, and not as its defect. Considering exoplanets on a galactic scale, we see them not as exceptional objects, but as a natural element of cosmic evolution, appearing, changing, and disappearing within processes covering enormous time and spatial scales. Exoplanets become the linking element between the physics of individual stars and the dynamics of the galaxy as a whole. At the end of this journey, one honest question remains. What exactly do we know, and where does the region of not knowing begin? Concluding the examination of exoplanets as a scientific object, it is important to turn to the question of the boundaries of knowledge and of how understanding is formed in this area. Exoplanet science develops under the conditions of fundamental limitations linked with the impossibility of direct observation of most of the processes of interest. These limitations are not temporary difficulties that technology will someday fully overcome. They reflect the very nature of remote cosmic objects. The main limitation is determined by distance. Exoplanets are located at distances at which only information transmitted by radiation is accessible. This radiation carries data about the system as a whole, but does not allow the contribution of the planet to be directly separated from the contribution of the star without the use of models and assumptions. Even in the most favorable cases, what is observed is not the planet itself, but the combined effect of its presence. Knowledge of exoplanets is always indirect, and this is not a weakness of the method, but a fundamental property of the very object of research. The interpretation of observations inevitably rests on models. These models are built on the basis of tested physical laws, but their application to specific exoplanets is attended by uncertainties. Many parameters of a system are either unknown or determined within broad ranges. As a result, different models can equally well describe the same data, offering, at the same time, different physical pictures. In such cases, science does not choose a single explanation by force, but preserves a set of admissible scenarios until new data appear capable of distinguishing between them. Most statements in exoplanet science are of a statistical character. They refer not to individual planets, but to sets of objects. A specific exoplanet may differ substantially from the average tendencies, and this is entirely normal. This is not a contradiction, but a reflection of the real diversity. The divergence between the individual and the statistical is an expected property of complex systems. The detection of an exoplanet does not mean a full understanding of its nature. In most cases, only a few parameters are known: mass, radius, orbital period. The remaining characteristics are derived indirectly and depend on the assumptions adopted. Even such seemingly basic properties as the presence of an atmosphere or of a solid surface often remain undetermined. This requires caution in formulations and a refusal of excessively concrete statements. The boundaries of knowledge manifest themselves also in the temporal dimension. Exoplanets are observed at one moment of their evolution, whereas their history covers billions of years. The reconstruction of this history is possible only on the basis of models and analogies. Different evolutionary paths can lead to similar present-day states, and therefore the past of an exoplanet rarely lends itself to unambiguous restoration. Science works with possible scenarios and not with precise chronicles. The terms applied in exoplanet science, Earth-like, habitable zone, atmosphere, are simplifications. They serve for orientation and classification, but do not reflect all the complexity of real objects. An awareness of the conditionality of these concepts makes it possible to avoid transferring intuitive expectations onto systems that may differ radically from everything we know from terrestrial experience. The development of exoplanet science is accompanied by a constant revision of ideas. New data often require the refinement or alteration of previously adopted models. This process is not a sign of the instability of knowledge, but the normal functioning of the scientific method, in which hypotheses are tested and corrected as information accumulates. Exoplanets serve as an example of an area where the dynamism of science manifests itself especially distinctly. There also exist fundamental limitations linked with the impossibility of experimental intervention. Exoplanets cannot be investigated directly by changing conditions or by setting repeatable experiments. All conclusions are built on passive observation and comparison. This brings exoplanet science closer to other areas of astrophysics, where knowledge is formed through the interpretation of natural experiments set up by nature itself. It is important clearly to distinguish what science can affirm with confidence from what remains an assumption. The existence of exoplanets and their overall diversity are reliably confirmed. The mechanisms of formation and evolution are described at the level of general principles, but the details concerning specific objects often remain undetermined, and this is not an omission, but an honest characteristic of the modern state of knowledge. Exoplanets also demonstrate that the expansion of knowledge does not lead to a simplification of the picture of the world. On the contrary, as data accumulate, ever more diversity and exceptions come to light. This requires a rejection of the striving for universal schemes and an acceptance of complexity as an inherent property of reality. Uncertainty is not a defect of science, but a characteristic of the very world under investigation. Regarding exoplanets calmly, without sensationalism, we see them not as objects of mystery or expectation, but as elements of a great cosmic process. They obey the same physical laws as the planets of our own system, but realize these laws under other conditions that we can as yet describe only approximately. Knowledge of them is formed gradually through the combination of observations, models, and revisions. This knowledge will always be incomplete, and it is precisely in this incompleteness that its genuine scientific value lies. Exoplanets are a space in which the limits of knowledge manifest themselves especially clearly. They show how science works with remote and inaccessible objects, relying on indirect data and probabilistic conclusions. An awareness of these boundaries makes it possible to perceive exoplanets not as a riddle demanding an immediate answer, but as a space for prolonged, calm, and attentive investigation, corresponding to the scales and rhythms of the cosmos itself. Write, please, in the comments how this story felt to you. It is truly important for me to understand whether it caught you. Do you think it is honest to call a habitable zone a region in which we merely cannot rule out life, rather than prove it? And tell me one more thing. Is it more comfortable for you to watch horizontal footage or vertical for the phone?